Okay, so last time I introduced so the general topic is polarization, and last time I introduced well, first of all, the idea of a linear base for polarization. So, in general, if we think of the xy axis as the axis perpendicular to the direction of propagation, which is z, we saw that we can decompose the electric field on two independent components. And we saw some special cases in which, depending on the relative amplitude of both Ex and Ey and the relative phase, you might end up with special cases about polarization. So now we move on, and we see that there's also an alternative base, which is more, which is better, which is preferable in the case of circular polarization. So I remind you, circular polarization means that the electric field describes a circle, which can be either rotating counterclockwise or clockwise, depending on which way. And to this aim, you define a new basis, which we call, you see the two unity vectors, here epsilon plus and epsilon minus, which are a combination of both E1, epsilon 1, and epsilon 2, which are the two instead, which form the linear base, the linear polarization base. So now, the one with plus sign is so-called right circularly polarized polarization unity vector, or positive helicity, while the one with the minus sign is also referred to as the left circularly polarized wave, or negative helicity. The reason is because you have to think of which hand reproduce the way the electric field rotates. I'm going to show you why this is indeed the case. So why are these unity vectors corresponding to the two different ways of circular polarization base? To prove that, let's consider the Euler formula. You know this very well. Euler or Euler formula depends. Euler was a Swiss-German guy, as you know, so I should say honestly Euler, but if I say Euler, then probably few people understand. So Euler formula. So if you consider, for example, the second term here, or either plus or minus I epsilon 2, then times the spatial temporal part, it means that plus minus I times means adding or removing in the argument of the exponential minus pi half, okay? Just like that. So in particular, if you collect I, it means adding for a fixed z, so if you fix a point in space, it means that just multiplying by this guy is kind of adding or removing 90 degrees phase. So it's interesting just to see why indeed one is right circular and left circular polarization wave. So let's fix a point in space. Just for simplicity, let's fix z to 0. Now, we study how the corresponding vector changes as function on time. So let's consider the first term here, for example, which is the same in both terms. So just epsilon 1 times, again, the wave term. So as I said, z is fixed to 0. So you see, I just showed the different four quadrature phases, and then this is, of course, the beginning is the same as the beginning. So when omega t is 0, 90 degrees, 180 degrees, 270 degrees, or just 360 degrees. So you see, epsilon 1 is the unity vector of the x-axis. So the x-axis in our mind is just the horizontal axis. So when omega t is 0, of course, all this guy is 0. So it means that the electric field component due to epsilon 1 is just this y, is just directed along the positive direction of the x-axis. When it is 0, of course, you have to take, here I didn't say, but of course you have to consider the real part of this guy. This guy is an imaginary object. So just consider the real part means the cosine of this of the argument, okay? So cosine of 0 is 1, cosine here 0, minus 1, 0, 1. So you multiply all these numbers times epsilon 1, and you get this vector. Now, let's do the same game with epsilon 2 now. So the very same, so you see immediately that the only thing that changes is just the unity vector. Here, you multiply the same scalar by a different unity vector, which is directly vertically, because it's along the y-axis. But now, for example, let's focus on this guy here, epsilon minus, so the left circularly polarized unity vector. So we have here we have epsilon 1 minus e epsilon 2. So we want to study minus I epsilon 2, and then the wave term. Now, as I showed you here, minus I times, look at here, minus is the bottom sign. So here above, the bottom sign is plus. So to know how this vector what it looks like, you just have to take the real part of all this guy here with the plus sign here. But this is equivalent, if you look at taking as the phase, instead of omega t plus 90 degrees. So it means that when you want to, here, you have to look at the previous case 90 degrees ahead. So 90 degrees means if you are looking for this one, you have to look this here. So 0, 0. And for this position, you have to look again 90 degrees for, in the previous case, 90 degrees ahead. This one is here. This one gets here, and this one here gets here. Just like that. There is a 90 degrees phase difference between this guy and this guy below here. And now finally, if you want to get epsilon minus, well, epsilon minus, look at here, is just the sum of the first guy here and the third row here. So the combination is just make a sum of the two vectors. So this guy plus this guy is this guy here. Null plus this one is this. This plus this is this. This plus this is this, and so on. Now, I remind you, we are looking at the way the electric field parallel to epsilon minus changes as a function of time for a fixed position in space. If you look at how this arrow changes as a function of time, you see that it's rotating clockwise. But now, you see x, y, z. So z is the direction of propagation of the wave. Now, if you imagine to point your thumb towards the direction of propagation, in order to have the fingers showing the way the vector, the electric field, rotates, you cannot use both hands. There's only one hand which works. So if you want to use your thumb pointing to the direction of propagation and the other fingers showing the way the electric field rotates, you necessarily have to use the left hand. Just try yourself. That's the reason why it is called left circularly polarized. And it's, of course, it's just something for kids to see that instead, if I instead had chosen epsilon plus, you would have had a counterclockwise rotating electric field. Counterclockwise rotating electric fields, you can have it only if you use your right hand. So that indeed proves the fact that when you have a component parallel to either epsilon plus or to epsilon minus times the wave term, you have either a counterclockwise or a clockwise rotating, which is reproduced by respectively the right hand or the left hand. Positive, negative helicity, it just reflects that in people's mind, whatever is related to right hand is positive and whatever is related to left hand is negative. This is not very fair to left-handed people like myself, so I don't particularly like this, but this is just the way, a matter of convention. So there's nothing negative with left hand, just a way of, just as a way of speaking. So indeed, this is indeed the case of left-handed vector. So you can describe whatever possible generic polarization instead of using the two linear unity vector epsilon1 and epsilon2, which are Cartesian vectors. So one is for the x-axis, the other for the y-axis. You can use, in a fully equivalent way, the composition, the linear combination of these two new, the circular polarization base. Okay, this is just an illustration of what I just explained. So you see indeed that if you are looking from the point of view of the direction where the thumb points, in order to have clockwise rotation, you have to use your left hand. And this is just what is shown here in this figure. Otherwise, of course, the right hand. If you think, for example, you have no circular polarization. Think of the special case of a linear polarization. So the electric field, for example, is oscillating up and down along the y-axis, for example. Well, how can this be expressed as a linear combination of in the circular polarization base? Well, very easy. You have two components with equal magnitude, the one multiplying epsilon plus and the one multiplies with epsilon minus, which are just in phase. So you can think of an electric field oscillating along the y-axis as the superposition, the sum of the two, one counter-rotating and the other, one clockwise rotating and the other counterclockwise rotating. In this case, mind that this is the left polarized wave, this is the right polarized wave, and the direction of propagation in this case, if you try to reproduce with your own hands, you see that the wave is propagating inward, so it's getting into the page, not out of the page. So you see indeed that the superposition of two, one with right circularly polarized and the other one left polarized wave, indeed the result, the sum is always along the y-axis. So indeed, even the case of linear polarized wave, you can express as a sum of two circular polarization. So this is, I think I've shown you that this is a fully equivalent base. So you can make a choice, either a linear polarization base or a circular polarization base. And you can, in any case, you can express a generic polarization as a function of either base. So you can also express a generic case as with a linear combination of the right and left polarization, each of which has its own phase. So the relative phase we will call for the plus, phi plus and phi minus, of course, for the corresponding, and the corresponding amplitude. So E plus and E minus are the corresponding amplitudes for the two circular polarization base. There are, again, here special cases. So, for example, if the two amplitudes are not equal, but, for example, if they have the same phase, so the relative phase delta phi plus minus is just 0, then you have an elliptical polarization whose axes coincide with the xy. And if you think for a moment, you can easily recover that. If instead, the most general case, the most generic case in which neither the amplitudes nor the phases are equal, you have the most general case for a monochromatic wave, for a single monochromatic wave. So we are still considering a very special case of a single monochromatic wave. You have the most general case, which is an elliptical polarization whose axes have nothing to do, are not co-aligned with the xy axis. And they are rotated, as I wrote here, by delta phi half. As a matter of fact, so this is the ideal case of one single monochromatic wave, which is produced by a single entity, so a single atom, for example, or by a set of atoms which are emitting coherently, so with a fixed relative phase. But actually, in real observations, what you see, what, for example, a detector like a telescope, if you are thinking of a kind of optical light, well, what you see is always the superposition of several different waves. Even at a given wavelength, it means that the radiation that you get is the result of different independent atoms, which work independently of one another. So the resulting electric field could cancel or just change in a random way the direction. When this is not the case, so when there is some when there is some direction which is preferred for some reason with respect to another one, then it means that you are, even when you consider the superposition of different waves, you're left with a non with a field, a resulting field, which has some which keeps memory of the preferred direction. So the electric field will be preferentially directed, will have a larger magnitude along a given direction with respect to another one. And when this is the case, this is very important piece of information, because this is telling you something about the way the electromagnetic wave was generated. So if there is indeed a preferred direction, it means that this is telling you something about the properties of the source itself. So by studying the polarization properties, particularly, of course, when there is hint for a polarization, for a non-zero polarization, it means that you can have very important clues. You can gain insights into the nature of the emission process, and so into the configuration of what in the source determines is responsible for the emission. We will see some examples in the well today, but also in the future classes when we will be considering several different radiative processes. So let's get to the point where we have to define the way, on a practical base, the way we measure, we estimate the polarization. So what we need is are so-called the Stokes parameters, after the name of the person, Sir George Stokes, who kind of 170 years ago proposed. So these Stokes parameters are nothing but 4 parameters which are related to intensities. These are just intensities. And this is very practical, because intensities, as a matter of fact, is indeed what you measure. You cannot measure, talking about an electromagnetic wave, you cannot measure the amplitude. But what you surely can measure is intensities. Power, energy per unit time for given direction. That depends on the way. So let's see how they are defined. In particular, they are defined as a function of, in terms of scalar products between the unity vectors that we introduced. They can be either the linear base, the linear polarization base, so epsilon1 and epsilon2, or alternatively, as we will see in a moment, the 2 unity vector of the circular polarization base, so epsilon2, epsilon plus, or epsilon minus. So let's see just the definition of these 4 guys. The first one is I, which is defined as the sum in quadrature of, you see, of the electric field scalar epsilon1 and epsilon2. If you remember the way it is defined, the electric field in the linear base, you immediately see that this is nothing but the sum in quadrature of the 2 amplitudes. So Ex squared plus y squared. So of course, I stands for intensity. The more intense the field, the correspondingly intense. But it tells you nothing about the possible difference between the 2 directions, x and y. You just see the sum. The difference is told you by the q parameter. Q is the same 2 guys, but instead of the sum, you have a subtraction. So Indeed, when Q is positive, it means that somehow the intensity and so the amplitude along the x-axis is dominating the other term. So, or when it is negative, of course, the other way around. So Q is telling you about the possible difference between the two axes. And then we have the third parameter, which is called U, which is defined this way. You see this strange R is just real part of, because the argument is an imaginary quantity. Because indeed, if you remember, E is defined as an imaginary quantity. So here you have to work out the scalar product takes the complex conjugate. Here the asterisks stands for complex conjugate, and then multiply by this guy here, and then you take all the real part of this twice. It's immediate to see again. I'm not going to show you. I invite you to verify that the second equalities here can be verified in a straightforward way. Just take E as a function of Ex and Ey. And you immediately see in this case that you come up with the mixed product and the cosine of the relative phase. Phi xy, as we will be defined in a moment, is just the relative phase, means the phi y minus phi x. And instead, the fourth parameter is called V. And by definition, you take the very same guy as before for U, but instead of taking the real part, this strange I means take the imaginary part, okay, twice. So again, you immediately understand that having to do with an exponential of an imaginary quantity, in this case you take the real part, you end up with the cosine of an angle. In this case, you take the imaginary part, so you end up with the sine of the same angle. So it's straightforward, but make sure you can prove this equalities. So this is the definition. The second equality is just something that you can prove. So where, yes, as I said, the relative phi is just phi y minus phi x. So these are four intensities, because they are all, from a dimensional point of view, if you pay attention, they are all magnitude squared, okay? So they are just all intensities. If you, now let's move on. If you invert the relation between the circular polarization base and the linear polarization base, we defined, if you get back a few slides ago, we defined epsilon plus and epsilon minus as a function of respectively epsilon 1 and epsilon 2. Now, if you invert this relation, it's just something for kids, you immediately see that you recover these inverse transformations. So now we have epsilon 1 and epsilon 2, so the linear base as a function of the circular unity vectors. So this is just something that you can immediately see. Now, the goal is, let's express the Stokes parameters as instead of as a function of epsilon 1, epsilon 2, Ex and Ey, and the relative phase, as a function now using the circular polarization base. How can you do that? Well, if you consider I in the previous slide was defined as, let's get back here. So the goal here, how can you do that? You replace, instead of epsilon 1 and epsilon 2, the inverse formula that I've just shown you, and I'm going to show it again in a moment. And instead of E, the electric field expressed in the linear base, you use the electric field in the circular polarization base. So if you carry out this exercise, you see that I, the intensity now, is indeed the result of this sum of these two terms, which is indeed the sum of the squared amplitude E plus E minus, which makes sense if you think for a moment. But apart from making sense, it's something that can be and should be demonstrated straight away from the way I told you. So I strongly advise you to check it out. So make sure you can prove this. It's just a matter of some algebra. But it's important to carry out at least once in your lifetime. What about Q? Well, Q, you see, it's twice the real part of this guy here. So you start from the previous definition, you replace epsilon 1 and epsilon 2 with epsilon plus and epsilon minus. You use E as a function of expressed in the circular polarization base, and after some algebra, you end up with this expression. So again, twice the real part of this imaginary quantity. You see? Well, I remind you the asterisk stands for complex conjugate. So indeed, you see, this is twice the product of the two amplitudes times the cosine of the relative phase, where here the relative phase is related to the two phases of the two unity vector base, so epsilon plus and epsilon minus. The very same comment can be made on U. So if you carry out the same exercise, you will see that U is nothing but twice the imaginary part of the same quantity. So again, for the very same reason, is the same guy as before. So instead of taking the real part, you take the imaginary, which turns into, instead of taking the cosine of the relative phase, you take the sine of the relative phase. As I said, I'm not going to prove it. It's just a matter of few easy calculations, but it's important that you can prove it on your own. I mean, it doesn't make sense. It wouldn't make sense for me to do this here, but it's straightforward. And what about the last parameter? The last parameter is instead, if you remember the way it was defined, Q was EX squared minus EY squared. So V plays the same role for the circular base as Q for the linear. So the V parameters tells you when this is non-zero, particularly, for example, when V is positive, it means that the component on the right circular polarization is stronger than the left circular one, or the other way around. So it's a completely equivalent way of projecting and describing the properties of your wave, of your monochromatic wave. Where, yes, the relative phase is just in this case phi minus phi plus. So let's summarize what we've come up with so far. So we have four parameters, which are four scalars, which are intensities. We defined in the linear base, and we also found the corresponding formulae for the circular polarization base. In particular, you see that there is a kind of symmetry. And in either case, you have two terms. Well, the intensity is just the same. Well, looks the same. Well, of course, they are the same, but they have a different look. While the difference with respect to the two polarization base units that you take is given in the linear base by I and Q, in Q in particular, the difference, while in the circular base is given by V. And the mixed term are given in the linear polarization base by U and V, while for the circular one by Q and U. So, just summarizing, I is the total intensity, Q, as I said, it tells you how X is prevailing, is dominant with respect to Y over Y, while V is telling you the same concerning the comparison between the two circular polarization wave, particular plus with respect to minus over minus. And then you have the two parameters, UV, which tells you about the relative phase, and QU, the relative phase concerning the circular polarization base. So this scheme summarizes in a quite effective way, I would say, the relation, the differences, and what is in common between the two ways of projecting, of considering the four parameters. First of all, if you consider a monochromatic wave, so in the case in which the relative amplitudes and phase are fixed, they're not independent. You can immediately verify in a straightforward way that indeed there is this relation. So the intensity squared is just the sum squared of the other three Stokes parameters. And indeed, it makes sense because you have 4 parameters. And if you think the same information, if you think of the linear base, is encoded in Ex, Ey, and delta phi. So you have 4 parameters as a function of 3 independent parameters. So it makes sense that they're not independent. There must be a relation between them. But this holds true as long as you consider a monochromatic wave with fixed amplitudes and phases. As I said, as I repeated, but I say it again, in actual observations, as a matter of fact, you see the sum of different independent waves. So the phase change as well as the amplitude can change in a random way, I would say, dependent on which kind of source you are considering. So in general, they are fluctuating. And fluctuating in a random way if the sources which are responsible for the resulting electric field are incoherently emitting, so independently of one another, while if they are somehow emitting with some degree of coherence, it means that they are kind of in phase or anti-phase, whatever. So in that case, you could end up with a non-zero polarization. So as a matter of fact, what you measure is time averages of the Stokes parameters. So this is indeed what, as a matter of fact, you measure. So with this symbol, of course, is an average, but in this case, is meant to be a time average, okay? So given that you measure the time average of the Stokes parameter of the superposition of different waves, the relation that you see above doesn't necessarily hold true anymore. So to express, as I said, in the most obvious case, in the simpler case of totally incoherent emitting source, you have essentially you have no polarization. You have, for example, Q is 0. Because if there is no preferred direction, it means that the average value along X equals the average value along Y, as well as the relative phase on average, the cosine, when there is no preferred value for the relative phase, is just 0. So Q, U, and V, in the most general case of no polarization, will be 0. So we define conveniently the so-called degree of polarization, which is just the sum, of course, squared. So square root of the sum squared of Q, U, and V over I. So you immediately see that if you consider one single monochromatic wave due to a single atom or just due to an ensemble of atoms which are emitting coherently, so with the very same fixed phase and relative phase and amplitudes, of course, P is 1. So that would be the highest possible degree of polarization. So when you have 100 degree or just 1, if you want to, usually people measure the degree of polarization in percentage. So 100% polarization is the highest value you can have. Means that the wave whose polarization you are measuring is fully polarized. So it's fully coherent. While, of course, in the completely opposite case, which is totally unpolarized wave, as the case I was mentioning, of course, all of the 3 parameters Q, U, and V are 0. So you have a degree of polarization which within uncertainties is compatible with 0. So unpolarized wave. There's also another way of looking at Stokes parameters. If you think of, again, let's consider the very special case of one single monochromatic wave with fixed fixed amplitudes and phase. So the most general, of course, this is a polarized wave, and the most general case is an elliptical polarization. So it means that the electric field will describe an ellipse. So let's imagine that you see the z-axis is the one here. The wave is propagating along this axis, the z-axis. So the electric field just lies on the xy plane here. So in the most general case of a monochromatic elliptically polarized wave, the electric field will describe an ellipse just lying on the xy plane. And in the most generic case, the angle between the main semi-major axis of the ellipse and your x-axis, we call this chi, as I already told you in the previous lecture, chi, the polarization angle. So the polarization angle tells you how this ellipse in this case is orientated with respect to your reference frame. So you can also express E as a combination of, you define two unity vectors, epsilon A and epsilon B, which correspond to the direction of the two axes of the ellipse. So with A is the direction corresponding to the semi-major, to the major axis, and B to the minor axis of the ellipse. So this base, this new base, epsilon A and epsilon B, is a kind of natural base, because it's just, you take just the two directions of the two axes of the ellipse. And times, of course, this is a wave propagating along Z, so of course you have this term. Well, conveniently, if you consider the rectangle in which the ellipse is inscribed, well, you can consider the two sides. So, for example, if we think of the, again, EA is the semi-side is a semi-major axis of this ellipse, and AB and EB is the semi-minor axis of the EB. You can define a beta angle. Beta is just such that essentially it tells you the proportion between the two sides. So beta, for example, is 45 degrees when the rectangle is just a square, if you think. And you can think of just the ratio between EA and EB, or better, the ratio between EB and EA is the tangent of beta. You can immediately see from here. So now I tell you that if you measure epsilon zero, EE0, sorry, as the sum squared of the two amplitudes, now the two amplitudes are related to the axis of the ellipse, I tell you this is exactly I. So the intensity as we define in the Stokes parameter. How can we see that? Well, just project the two unity vectors, epsilon A and epsilon B, on your linear base unity vector. So epsilon 1 is just along this axis here, and epsilon 2 is just along this axis. This is just something for kids, you know, from your very first year of undergraduate courses. This is just a rotation of the two bases. And looking at that, of course, the rotation angle is just the polarization angle, chi. Now, if you remember that the electric field can also be equivalently expressed in the linear base, so Ex with the relative phase plus Ey with the relative phase. Now, you immediately see that if you replace, instead of epsilon A, epsilon B into here, and then you equate everything which multiplies epsilon 1, everything which multiplies epsilon 2, you end up with this relation between the X and Y component and relative phase and the magnitudes of the electric field in the ellipse base, and as a function of the polarization angle. So you immediately see that when you square, if you remember the definition of I is Ex squared plus Ey squared. Well, you immediately see that this guy squared, the modulus squared, because this is, in general, of course, is an imaginary quantity, plus the modulus of this guy here, you see that you end up with EA squared plus EB squared. So indeed, I proved that the intensity can also be expressed as the sum of the squared magnitudes along the two components. Yes, indeed, this is what I just said. If you go on, for example, you immediately see that you can recover all of the four Stokes parameters as a function of the new quantities. So, well, it's not only as a function of the intensity, which is E0, but also as a function of both the polarization angle chi and also the angle that we call beta. For example, if you can just verify it straight away. If you remember, Q was defined as EX squared minus E epsilon squared. So you take EX squared minus E epsilon squared, you see that you end up with E squared, EA cos, and you remember cosine squared minus sine squared is cosine of the double angle. So if you remember all these very trigonometric identities, you immediately come up with all of the four parameters. And the advantage, you see, is that you can immediately exploit in this relation, you can immediately measure, you can derive from an experimental, an observational point of view, the polarization angle. For example, let's suppose, okay, the intensity is something that you measure immediately. But let's suppose that you can measure the intensity along all the possible directions. For example, if you have a polarimeter, something which selects, which allows the electric field just with a given direction to get through, you rotate the polarimeter and you make many measurements. So you measure, it's like rotating the XY axis with respect to. You see that the maximum intensity on a given axis is measured when, look at that, for example, when chi is 0. When chi is 0, you immediately see that you will have the maximum value for Q, but Q is the difference between the intensity along one direction and the opposite one. So if you can work out by rotating your polarimeter and making measure of intensities by rotating all the polarimeters, you see the angle at which you have the maximum difference. But the maximum difference means that the angle at which you have Q, which is maximum. But Q is maximum when chi is 0. It means that you have orientated your XY system parallel to the system of the ellipse. So from a purely observational point of view, it's easy to recover chi. But once you know I, you know chi, you can immediately measure beta. And once you know I, which is E0, E0 squared, chi and beta, you know all of them. So this is just a recipe, practical recipe to measure. So it's just a matter of measuring intensities just by selecting the polarization direction for all possible values. Of course, as a matter of fact, in practice, you will have a given pace. You cannot measure all of the possible angle, but for example, for a given, the finer the pace, the angular pace, of course, the better the angular resolution, so the better accuracy, the correspondingly better you know chi. So, okay, this is just a relation. If you just, again, some trigonometric identities. So for example, once you know, if you know U and Q, just work out the ratio. U over Q is just the tangent of 2 chi. So you can extract 2 chi as a consequence. Or for example, if you know V and I, just work out the ratio. And beta is nothing but 1/2 arc cosine of this guy. Another very important parameter is the so-called L, which by definition is called, L stands for linear polarization, which is Q squared plus U squared. Now, if you look at here, Q squared plus U squared, you see that if you look at the 2 chi, you have cos squared plus sine squared, so this guy gets away. So you're left with E0 times cos 2 beta. This tells you the linear polarization. What does this mean? Well, this is telling you how stronger the A direction is with respect to B. In the extreme case of a largest possible, for a given intensity, of the largest possible value for L, it means that beta is 0, for example. When beta is 0, this L is maximum. But beta 0, it means, you see, it means that EB is 0. It means that it's no more an ellipse. It's just oscillating. So all the electric field is fully along the A axis. But that's indeed the case of maximum linear polarization. In the most general case in which beta is no more necessarily 0, but is for example, it is not 40 degrees, 45 degrees. Because if beta is 45 degrees, you see that both components, EB and EI, are equal. So in that case, L is 0. Linear polarization is 0. It means that there is no preferred direction between A and B. To summarize all the possible combinations, I made this table, which I like it particularly, because it tells you, you see, you have essentially different combinations of information that you can get from the parameters. For example, we define L, we have V, and I remind you, V in the circular base is E plus squared minus E minus squared. So when V is positive or different from 0, it means that there's one circular base term prevailing on the other one. So let's have a look at all the, so you have two parameters here which are relevant, V and L. Of course, L depends on Q and I, on Q and U. But if you consider all the possible cases, where case means either equal to 0 or non-zero, you have two variables, two possibilities. So the Cartesian table of all the possible combinations is just four cases. So let's consider all of them. When V is 0, it means that when you project the electric field on a circular base, there is no preference for the two polarization, just as much in the right base as well as in the left circular base. So it means that V0, it means that here the sad phase means, oh, no circular polarization. While when L is different from 0, it means that there's one direction which is prevailing over the other one. So there is some degree of linear polarization. One direction is stronger with respect to the other perpendicular one. So the electric field tends to be preferably stronger on one direction than the other. So linear is happy. So in this case, V0, L non-zero, you have some degree of linear polarization, no circular polarization. Of course, you can immediately appreciate the opposite case, in which the only parameter which is non-zero is V. If L is 0, it means that, as I said before, both components on average along A and along B are equal. So it means that there is no direct preferred direction. So no linear polarization at all. L0, so the phase for the linear case is sound. But instead you have V different from 0. So for some reason, E plus or is taking over E minus or the other way around, depending on the sign of V. So in that case, you are in the presence of some degree of circular polarization. Of course, the most uninteresting case is the case in which you have no polarization at all. So if you look at the definition of L, it means that V, Q, and I, all of them are 0. And we already know that in this case, the total degree of polarization is 0. No polarization at all, neither linear nor circular. While in the last case, in which both parameters are different from 0, what does this mean? Well, okay, this is just completely unpolarized. This is elliptical. If you have both linear and circular, that's exactly the case for example, for the trivial case of a monochromatic wave. Due to a coherent ensemble of atoms, of course. So the relative amplitudes and phase are constant, so you are indeed in this case. And in which case, of course, you have all of them are non-zero, and so the most general case is an elliptical polarization. We will see, as I said, when today, we will begin today even, the review of the most important radiative processes in astrophysics, but not only in astrophysics. We will see that in several cases there are degrees of polarization, depending which kind of polarizations, and how important, how informative this can be. I will show you just a very brief example. I'm not going to talk about this, so this is an astrophysical example in which I myself was involved, and I'm still involved. So please forgive me if I chose a topic which really concerns my lines of research, but I think it's fair. Um, so this is the measure of polarization of something related to GRB. GRB is an acronym which stands for, as you see here in the title, gamma ray burst. Gamma ray bursts are cosmic explosions, very powerful, extremely powerful explosions in which there is the emission of a jet of ultra-relativistic matter. So you have the expulsion, the emission of matter, which is expanding at ultra-relativistic speed. And for some, according to some mechanisms that we still have to exactly understand, at some point there is the emission of gamma rays. These bursts of gamma rays last typically several seconds. And nowadays, we know that there are two kinds. In particular, one of them is associated with the death, with the collapse of the core of very massive stars, which are also rotating. So not all of the massive stars that end their life end up with a gamma ray burst. We know that there is a supernova, but in a very few percent of cases, in addition to the supernova, this jet of ultra-relativistic matter which produces gamma rays. Now, we still have to understand exactly the structure of the, so what's the process responsible for the emission of these gamma rays? What makes these gamma rays? Where do these gamma rays come from? Of course, these are gamma rays, but I didn't say, but in the minutes after the gamma ray, when the gamma ray burst is over, you have some also radiation at longer wavelengths, the so-called afterglow. Afterglow means what comes after the glow, what comes after the bang, after the explosion. So this is longer-lived radiation at longer wavelength, in particular in the optical. And for the first time, a few years ago, my group, for example, was able to measure the optical polarization within a couple of minutes, just a couple of minutes after the burst. So you don't know when a burst is gonna go off, because first of all, you don't know where the position in the sky. So you have to be quick enough. When you know there is a gamma ray burst, you have to point your telescope and just to carry on your measures. In this case, of course, you are talking about relatively faint optical sources, so you need a big telescope. We had, and we still use, a robotic telescope of 2-meter diameter with a polarimeter at its focus. And this polarimeter was able to measure prompt optical polarization of the light, of the optical light, just starting from 2 minutes after the burst. This is very important. Why? Because we measure, if you look at this, so this is the figure, this is just the source that, I didn't tell you, but these gamma ray bursts are so powerful that we see them even if they are the furthest objects of stellar scale in the universe. They are so bright that we see them at such large distances that you can only see typical galaxies and also bright galaxies. But these are stars. These are just explosions due to single massive stars. So the energy emitted is something really mind-boggling. Of course, we know the number, but here, if you want to learn more about gamma ray burst, of course, I advise you to attend my optional course on multi-wavelength, multi-messenger astrophysics, but this is another story. So here, the point I want to make is that we measure that, you see, in the y-axis is the degree of polarization, degree of linear polarization in percentage. All these error bars here are stars within the field, which are numbered. So you see number 3, number 1, number. The GRB, which is in the image here, is this guy here, has a degree of polarization which is significantly much higher than the other field stars. And you see here around 20%. 20%, as I will show you also in the next classes, is huge. It's it's a high degree of polarization. In particular, we studied how the polarization degree here varied as a function of time. This is time in log scale, in seconds. And here is the polarization angle. Well, this is in the bottom panel, you just see the flux. The flux was decaying, but I don't care about this. Look at these two at the top panel and the middle panel. The top panel is telling you the polarization degrees. So you see that you see a slight decrease as a function of time, and the polarization angle. So how the preferred direction of the electric field is orientated with respect to your reference frame was fixed, didn't change. I'm not going to tell you why, but all this pieces of information is strongly suggesting that there must be a large-scaled magnetic field ruling the emission of this gamma ray burst. This is extremely important because before these measures, we didn't know exactly the role, how much energy is carried away by a point influx vector associated possibly with a magnetic field, which is a large-scale structure. If you want to appreciate in full detail the impact and the consequences of this discovery, you have to, of course, to study more about gamma ray burst. But this is just a hint, a way of proving how important. In this case, we explored a part of the physics involved which is not explorable otherwise. So the polarization, when you can measure polarization, you can get really important clues about the source. And this is just a picture telling you exactly the kind of information. So this is a paper that was published a few years ago on Nature. So it's telling you, okay, there is the emission of a jet of ultra-relativistic matter, and in train with this jet, there is a magnetic field, large scale. So these lines just want to show you a large scale order magnetic field. So not a magnetic field which is randomly generated by turbulence, for example. We know from basic physics that when you have some turbulent medium, you can have you can have some magnetic field just due to the turbulent motion of charges. In this case, there's nothing like that. So the progenitor star, so the star that is working there, must have the capability of making a large-scale magnetic field. And this exhausts all the topics I want to talk to you about polarization. So this, again, here you have two lists, one about the general textbooks that I used, and then particular Longueur in this case, and then also a list of papers devoted to polarization of gamma ray burst, which is maybe a little bit more specific, but if you want to know more about that, that's it. Oh, these are all hyperlinks about the papers. Whenever you see the reference to papers, you see if you also on the PDF, when you go with the mouse on the way you click, you get to the paper. Okay, so I still have kind of 20 minutes, let's say, or more or less. So let's begin the new topic, very broad, which is gonna keep us busy for 1 month, more or less, which is lecture number 6. Okay. Why? Oh, I already shared the PDF, by the way. Why is this so huge topic? Well, because you see, this is the family picture, a lot of names, some of which are probably familiar to you. You probably have seen them in other contexts, or are not, surely. So these are the main radiative processes that we will review, we will study, we will learn more about in the next classes. And all of them are very relevant in any astrophysical contexts, but not only in astrophysics, as you will see. So to learn them very well is something that you can benefit also in very different contexts. So let's begin this journey. So this is the core of the entire course. So radiative processes, I don't want to say it's the most important, but surely if I have to choose the core, So the most relevant, the one which is connected with all the other parts, this is indeed the radiative processes part. And you see, we studied radiative transfer. Now we will make use of what we've learned in the radiative transfer here to appreciate in full detail all what is about. So let's start with Thomson scattering. So what is this? Well, the ingredient is that you have a single electron, for example. By single, I mean an electron which doesn't belong to any atom. So it's a free electron. It's no more bound electron. It's a free electron. And you can think of this as a stationary electron, or in any case with a non-relativistic electron. So let's consider a stationary, steady electron. So an electron which initially is not moving. The goal is to find out how it responds to a plane electromagnetic wave, which is just crossing, which is coming up. But you immediately see that an electromagnetic wave has a wave which is electric and magnetic field, in particular, something which can accelerate the electron. But you know very well that an accelerating electron means an electron which is emitting, Larmor's formula. So you immediately see these two aspects. A wave which is transferring energy to the electron, because by accelerating it, it means that it's making a work on it. So the wave transfers energy to the electron, but the electron itself also emits energy because it's a charged particle which is accelerating. So let's study the mathematical detail of this. In particular, we have to make another assumption. Let's assume, okay, I'll comment later on. So first of all, so I wrote, of course, the force exerted by the electromagnetic field of the wave on the electron. E is the charge of the electron, okay? Small e. Well, capital E is, of course, the electric field. You immediately see that, having said that this is in the Gaussian system, of course. So you have the Coulomb term plus the Lorentz force. You immediately see that having to do with a non-relativistic electron, it means that V over C is much smaller than 1. If you compare the magnitude of the two terms, it means that this one is much stronger than this one. Because if you remember, in a plane wave, E has the same magnitude as B. So these two guys have the same magnitude. But V over C is much smaller than 1. So it means that overall, the Lorentz term is negligible with respect to the Coulomb term. So you can approximate the resulting force acting on the electron as just EE. So the electron's charge times the electric field of the wave. Let's express more in detail what the electric field is. Well, this is a plane wave. So it has an amplitude which we call E0 times, of course, the sign of the corresponding pulsation of the wave. So the frequency of the wave, which we call omega zero. Now, let's apply, of course, Newton's second law, just like that. So this is the resulting force acting on the electron. So this is just m times the acceleration of the electron. So the acceleration of the electron, which I call A here, is just this guy over m. Epsilon here, I didn't say epsilon is the unity vector along which the electric field oscillates. Okay. So of course it's perpendicular to the direction of propagation of the wave. Now, what is the plan? Why am I so interested in the acceleration of the electron? Well, you know very well, I want to calculate the power emitted by the electron, so I need to go through Larmor's formula. In particular, you know that I need the modulus squared of the acceleration. Here I calculated, you see, modulus squared, and then I take this average value. What does average mean? Well, you see that the acceleration is a function of time. In particular, is a periodic function of time. So I want the time average. So the value averaged over a period. But you know very well that if you square this guy, you have sine squared. The only term that depends on time is this, the sine of this guy here. So the average of sine squared is 1/2. So the time average value of the square modulus of the acceleration is just e squared, e0 squared over m squared 1/2, where 1/2 comes from time averaging of the sine squared, okay? Now, I want to study both the dependence of the energy of the power emitted by the electron as a function of direction, but this is something that we already know. If you get back to what we derived in the case of the power emitted by an accelerating charge, you remember that the power as a function of direction, so dp over d omega, is just e squared, the charge squared, modulus acceleration squared. In this case, I'm taking the time average, over 4 pi c cubed, and then the term which is telling me about the direction. So the sine squared, if you remember, of theta, where theta is direction between the direction of the propagation of the wave and the direction of the you are looking at. So in this case, of the where you are measuring the emission and the energy emitted by the electron, which replacing the value, the time average of the squared modulus of the acceleration is just this guy squared. So e fourth e squared. Okay, here there must be a is e fourth. Here there's a typo. Is e0 fourth, of course, over 4m cube squared, and yes, also here there must be m fourth power. Now, the total power, if you integrate over the entire sky, of course, you know that very well that by integrating sine square, you have 8 pi over 3. This is something that we saw so many times. So again, by integrating this way, you end up with, or in any case, you know very well the Larmor's formula over the entire sky. So 2/3 acceleration squared over c cubed, which is indeed this guy here. No, before I made a wrong comment. Sorry, it is okay as it is written here, because this is already the modulo square of the acceleration. So indeed, this is the e fourth comes from this term here times this times here, but then the rest is okay. So there's no typo. It's correct. So okay, so this is just the power emitted as a function of direction, and again, Larmor's formula, having calculate the acceleration, the corresponding power, time averaged power, okay? Because the acceleration is a function of time, so is the power. We take the average, time average value, so just like that. So again, you see immediately that the power emitted by the electron scales in particular with the intensity of the wave, E0 squared. Now, let's calculate the Poynting vector of the wave. If you remember, this is a plane wave, so is c over 4 pi modulo squared of the electric field. But again, here I want to take the time average. So again, time average of the sine square, I gain an extra factor of 1/2. So c over 8 pi E0 squared. Now, as I was commenting at the beginning, you can look at this process in this way. You have energy coming in from the point of view of the electron. You have energy coming in. So the electron is receiving energy from the source, from the wave, and is indeed emitting energy because it's accelerating. You can see this process of absorption and emission as kind of scattering, because then in the end, the electron keeps accelerating the same way, so its energy then is the same. So when the wave keeps on accelerating and the electron keeps on emitting, at some point it looks like the electron is just scattering the radiation which is just crossing it. In particular, you see, dP over d omega is power per unit solid angle. Power, you can see power as flux, which is the Poynting vector. The Poynting vector is power per unit area. So you can see this as this the flux. So the Poynting vector times an area, which we call d sigma, over d omega. So in a way, we can see the process of the electron acting as something which is scattering radiation. And this radiation is scattered towards all the possible directions. So we want to measure, we want to characterize its capability of scattering radiation as a function of direction in terms of a cross-section. But this cross-section must depend on the direction. So d sigma over d omega, it's called a differential cross-section. To better appreciate this aspect, I made this drawing, the scheme. So let's suppose this is just the plane wave, both fields, with which a given Poynting flux is associated. I remind you, Poynting flux is energy flux. So is power, so it's energy per unit time, per unit area. Now, this wave just meets the electron. The result of the action of the wave on the electron is that the electron will be accelerated up and down, given that I chose as the vertical direction the direction of the electric field. So the electron, as a result, will be accelerating up and down. But this process is, we know very well, and we know how much energy I just showed you, I just reminded you, we already knew from the previous classes. We know that the action, the result of this electron acceleration is the emission of energy as a function to all possible directions. So for example, let's focus on the amount of energy which is emitted along this solid angle d omega. So if we multiply dP over d omega times d omega, of course, is the power, so energy per unit time emitted by the electron within the solid angle. But you can think this as, so this is power. You can think this power as the result of flux, which is just coming through the electron. The flux is energy per unit time per unit area times an area which must correspond to that solid angle. So the capability of absorbing or scattering of the electron, scattering a given amount of energy towards that direction. So if you divide both sides by d omega, you immediately see that you automatically define the so-called differential cross-section. So the differential cross-section is just the capability. It's just, well, from a dimensional point of view, is an area over a solid angle. Multiplied by the incoming flux on the electron, it gives you the power scattered by the electron. So you can see this process as just energy which is scattered by the electron. Okay? The electron receives energy, and this energy then is emitted. So the budget is that the electron is redistributing the energy which is going through it. And we characterize this processing by characterizing the differential cross-section. So let's work it out. Because you see, we know we just calculated both dP over d omega, and also we calculated the Poynting flux. So we have all the ingredients, all the information to calculate the differential cross-section of this process. And in particular, I just replaced, instead of the average value of the Poynting flux, what we obtained a couple of slides ago. So we found that the average value for the Poynting flux is just c over 8 pi E0 squared. But we also know dp over d omega. If you get back, you see that dp over d omega is just e fourth E0 squared over all this guy sine squared. Again, this angular dependence is very important, as is what we already knew from the very first time we learned Larmore's formula. So you see, I used my knowledge. I'm exploiting both the knowledge on this term as well as on the Poynting flux. So the only unknown which I'm left with is the differential cross section. In particular, you see that the E0 squared just cancel out on both sides, as well as 8 pi. So in the end, d sigma, the differential cross section is just E fourth over m squared c fourth. And then again, there's sine squared dependence on theta. Now, let's have a look at the meaning of this. This is just the same sketch as previous, but seen in a slightly different way. If you remember, the electron is here. The wave is propagated through this direction. It's propagating horizontally. The electron is accelerating vertically. So if you remember the meaning of theta, theta means, okay, you are measuring the radiation going out this way. Well, theta is the angle between the acceleration of the electron and the generic direction. So indeed, theta is this guy here. But the electric field, I remind you, the electric field is oscillating vertically. So if I call epsilon as the unity vector of the direction, so it means that the electric field is oscillating this way. But this means that the wave that I'm considering acting on the electron is a linearly polarized wave, because I'm considering the case of the fixed direction along which the electric field is oscillating. So this explains why I put this as subscript here. Pol means this is the differential cross-section in the case of a polarized wave. So this is a special case. When a polarized wave, when a linearly polarized wave just crosses a region where you have a free electron, well, that's the differential cross-section. So you immediately see the result. One thing to note, there is a sine squared theta dependence. So the ability of the electron to scatter radiation depends on the direction of scattering. You see? The highest, the best capability is for scattering with a perpendicular direction when the theta is 90 degrees. So in this case, in the same direction as the moving wave. But here you see, this guy has to be an area squared from the point of view, from a dimensional point of view, because this is an area. So this has to be an area, not R squared. So L squared, a length squared. And this is indeed, there's a quantity which is very important, which shows up. So in the case of an electron, we're still considering an electron. This is called Re, called the classical radius of the electron. And it is defined as its charge squared over its rest energy, mc squared. It's immediate in the Gaussian system is straightforward to see that this is indeed a length. Because if you think that of the potential energy, charge square over distance is energy. So in this case, you have energy times length over energy. This is a length. And this is very important also to know. This is very important to know, to remember the formula which defines the classical radius of the electron, as well as its value, 2.8 10 to minus 13 centimeter. Now you see the classical radius of the electron squared times sine squared. Now if you don't care about the direction of the scattering, you want the total cross section, Well, the total cross-section, you just have to integrate of the solid angle, the differential cross-section. But again, if you have to integrate of the entire solid angle, something which depends on sine squared, you by now you know by heart, I'm sure, the integral over the entire sky of a sine squared is 8 pi over 3. So the result, the total cross-section, in the case of Thomson scattering, is 8/3 pi radius of the electron squared. This is so important that it has been given a name, which is denoted with sigma t, where t stands for Thomson. So 8/3 pi radius, classical radius of the electron squared, is the so-called Thomson cross-section. Its value in centimeter square is 6.65 10 to minus 25. I would ask you to remember this quantity. This is hugely important in electromagnetism, and whenever you consider phenomena in which matter, in particular in this case electrons, interact with radiation. You see why this is called also classical radius, because you see that sigma t is telling you about the capability of an electron of scattering radiation. So if you have a very classical and to some extent naive picture of an electron as a kind of small sphere, in this works as the cross section of the section of the sphere, as seen from the point of view of a wave, of an electromagnetic wave, or from the point of view of a photon. So when you wonder, I have some photons and I have some free electrons, how can I evaluate, even from an order of magnitude estimate, how can I evaluate how frequently they can interact? Sigma Thomson. Thomson cross-section tells you, let me use not very rigorous words, but just to let you understand, is telling you how big an electron appears from the point of view of a photon. So a photon will see an electron as big as the Thomson cross-section. I have to say, provided that the energy of the photon is not too large. If you consider photons whose energy is comparable with the rest mass energy of the electron, things will change. So the assumption here is that the photon's energy is negligible with respect to the rest mass energy of the electron. In this case, we'll see that, okay, before moving to this, what the scattering is a kind of coherent scattering, in the sense that the energy of the incoming photon doesn't change. The only effect is that photons that before scattering are traveling all along this direction, then will be scattered to all directions possible, according to the sine squared theta pattern. But the wavelength of these photons won't change. So in this sense, you can call it as coherent. You have no change in the wavelength of photon, only direction of these photons change. But this holds true, and this is the domain of validity of Thomson scattering, as long as the energy of the photon is negligible with respect to the rest mass energy of the electron. So you also see another aspect in which you immediately see why, for example, you could have asked, why didn't you consider protons instead of electrons? Do you have a preference, or didn't you like protons? No, it's not that. But if you look at the way the classical radius depends on mass, so you see it's inversely proportional to mass. But what matters is the cross-section. The cross-section is the radius of the electron squared. So the cross-section scales as 1 over m squared. So both proton and electrons have the same charge. So the numerator is the same. But the electron has a mass which is nearly 2,000 times smaller, which squared means 4 million times. So the corresponding cross-section of the proton is 4 million times smaller. That's why if you have a sea of protons and electrons, and an electromagnetic wave comes along, all the photons of the electromagnetic wave will be scattered by electrons, not by protons, because the corresponding cross-section of protons is 4 million times smaller. That's why we care mostly about electrons, okay? There's another important property of Thomson scattering, which is the capability of polarizing radiation. We can think of, so far I showed you here, okay, again, the differential cross-section of Thomson scattering for a polarized wave. What happens if instead of a polarized wave, I have an unpolarized wave coming across the electron? Well, here you can use a trick. You can consider an unpolarized wave as the superposition of two independent waves. Two independent waves, one perpendicular to the other. So, for example, you see in this drawing, you can consider a generic unpolarized wave as the sum of two independent fields, one oscillating along epsilon 1 and the other one oscillating along epsilon 2 in an independent way. So you can wonder, well, having called k as the unity vector corresponding to the direction of propagation and unity vector corresponding to a generic direction of the scattered radiation, well, you can describe the resulting differential cross-section of the unpolarized wave of the sum of the two contributions. Given that they are equal contribution, because no one is taking over the other, so it's just 1/2 of the sum of the two cross-sections. In one case, you have, if you consider the vertical component, the one with epsilon 1, well, we already saw that when the angle is theta between n and the vertical position, theta, we just derived in the previous case the formula here, which I put in red. What in the other case? Well, in the other case, if I call alpha the scattered angle, so the angle between the direction of propagation and the generic position, you see that I can use the very same formula. Now, the angle between epsilon 2 and n is 90 degrees. So it means that I can use the very same formula as before, taking the special value of 90 degrees. But given that this scales as r squared sine theta, and this is just 1 plus sine theta, but in this case it's more convenient to express as a function of alpha. So alpha sine theta is cos alpha, so cos square alpha. And this is indeed now the differential cross-section of the Thomson scattering for an unpolarized wave. And of course, if you integrate this over the entire sky, it's no wonder that you come up again with a Thomson cross-section. So the total, of course, the only difference concerns the differential cross-section between the polarized case and the unpolarized case. The total cross-section, of course, is always the same, the sigma Thomson. A few things worth noting is that you see the dependence on alpha is symmetric with respect to the scattering angle. Yes, if you take alpha or pi minus alpha, you get the same. So there is a symmetry between backward scattering and forward scattering. And the second thing is that the property of Thomson scattering is that the scattered radiation is polarized even in the case of an incoming unpolarized wave. Why? How can I see that? Well, imagine you are here. You are the observer corresponding at the vector n. If you project, you are here, you are looking at the radiation from this point of view here. If you're looking at the electric field from this point of view, you see that epsilon 2 is always the same because it's completely perpendicular to the direction. But the projection of epsilon 1 onto this guy scales as sine theta or cos alpha. So it means that as seen from this direction, you see this direction, which is a stronger magnitude from your point of view than this one. Okay, this is just a figure showing you the two patterns, the two components. So this is the scattering of one sine squared theta when you consider the component of the electric field oscillate in this way and one in this way. So the sum is just this 1 plus cos squared alpha, which is this kind of peanut-shaped, which is just the result. One can see it as the superposition of these two patterns corresponding to the two different independent polarization. But the point I wanted to make is that indeed I max, the polarization degree, is the maximum intensity you have in one direction minus the minimum one you have in the other direction. And this tells you the polarization degree. And if you look at this drawing here, this figure here, you see that this is 1, and this is the intensity, the projection of the electric field that you see perpendicular to this direction is this guy here. So sine theta intensity, sine squared theta is cos alpha squared. So indeed, this is just 1 minus cos alpha squared over the sum. So the important point here is that indeed Thomson scattering can polarize. So even if the incoming radiation is unpolarized, you get polarization. And this figure here, this is the figure of a region in the area molecular cloud where you have some star formation going on in the infrared domain. You see that this map, these lines tell you the degree, the direction of polarization of the infrared light. And indeed, the source of light is here. And all this light that you see is light which has been scattered towards you. And the structure of you see that all the direction of the electric field, which is kind of surrounding. If you look at the geometry here of this guy here, you immediately see why. Because you see the net polarization which is taking over of this direction with respect to this one. So if the source is emitting a photon that way, but then an electron scatters towards you, with this geometry, you see a polarization like that. So you immediately see that this pattern of polarization, of direction of polarization, is indeed the signature of Thomson scattering. And this is just an example of Thomson scattering. The very last point I want to make is a comment on the difference between Thomson scattering and Rayleigh scattering. What is the difference? Well, in both cases, the energy of the photons is negligible with respect to the rest energy of the electron. But there is an important difference. In the case of Thomson scattering, as I remarked at the beginning of this class, we are taking free electrons. When you consider instead Rayleigh scattering, the Rayleigh scattering is the scattering of a photon having the same characteristics as in the previous case, but electrons responsible for the scattering belong to an atom. And all the electrons belonging to a given atom work together in the scattering process. And indeed, if you think of the most important effect, I would say, so it is called also coherent scattering, coherent meaning that all the electrons belonging to a given atom work on the photon in the same way, in a combined way. They work together, so in a coherent way. So indeed, you know very well that the Rayleigh scattering is the explanation for the reason why the sky is blue. Because if first of all, you see that here theta is the scattering angle. You see that you have the same dependence as the Thomson scattering. But in particular, you have the dependence of 1 over lambda 4. Lambda is the lambda of the photon. So in particular, it means that the capability of scattering radiation is stronger for shorter wavelength. And indeed, if you consider light, it means that blue photons are scattered by the air molecules in a much more efficient way than red photons. So it means that when I look at the sky, I see many more blue photons which have been scattered rather than, because Rayleigh scattering is more effective for blue photons rather than for red photons. That's the reason why you have so blue scattered photon dominating over the red scattered photons. But this is important. So the difference is not about, because in both cases you have the energy of the photons, which is negligible with respect to the energy, to the rest energy. But the main difference is Thomson scattering, the one we studied, free electrons. So in the region that I showed you in the cloud, in the Orion cloud, you have to consider ionized medium, so free electrons. Instead, in the case of the atmosphere of the atmosphere, you have bound electrons. In that case, you have Rayleigh scattering. Okay, that's all for today. So we keep on. Next topic is Bremsstrahlung, which I really like. Well, I like all of them, and we will talk about this on Wednesday. Any questions?
No, thank you.
Okay. So, see you.